Yeah, go ahead. Thank you.
This meeting is being recorded.
All right, so let's start. Hello, everyone. Welcome to the webinar series on rate splitting multiple access 2022 to 2023. This webinar is organized by IEEE ComSoc WTC Special Interest Group of RSMA. So this is our last webinar, and it's our great honor today to have Dr. Wang from Huawei as our distinguished guest speaker. I believe most of you are excited as me to hear the industry perspective from Dr. Wang about rate splitting as well as its future. All right, so please allow me to make a brief introduction of Dr. Wang. Dr. Wang received a bachelor and a PhD degrees in electronic engineering from Zhejiang University, Hangzhou, China. He joined Huawei Technology Shanghai in 2008, and from 2015 to 2016, he was with Huawei Technology Sweden, and from 2019 to 2021, he was with Huawei Technologies UK. He has contributed to 3G, 4G, 5G physical layer standardization work and held numerous standard essential patents. Okay, so his current research interests primarily focus on developing future wireless communication standards such as 6G. So before the talk, I would like to remind the rules of our webinar. And during the 15-minute talk, please keep yourself muted and you can type your question in the chat box. And after the talk, we will have an around 10-minute Q&A session, and you can unmute yourself to raise your question, or I will choose 2 to 5 questions from the chat box. Okay, so enjoy the talk. And let me try to end my sharing screen. Okay, so Dr. Wang, you can start sharing your screen.
Okay, thank you so very much. Okay, yes, okay, issue.
Hi, Dr. Wang, we can already see your screen. Sorry, you are muted.
So it should be okay.
Yeah, but the screen is not for the slides. Yeah, now it's fine. Maybe you can use full screen mode.
Okay, very good.
Perfect.
Yeah, thank you. Yeah, so I will start my talk on rate splitting for 6G multi-user Mimo. So this is outline. So basically we have 4 points. First, I will raise the questions on network spectral efficiency, which I think is a critical problem for 6G and even for 4G and 5G. So we have done a lot of solutions to address this issue. Then we will review what happened in 3GPP, especially for 4G and 5G, to see what they responded and what observation we can make and insight we can get from their behaviors. And then I will review a short review what happened in research related to network spectral efficiency and what observations we can get. And last point is about the RSMA, actually, the focus of this talk. So I will talk about opportunities and challenges for 6G and Mimo. So let's go to this topic, network spectral efficiency. So we can see from the figure, I think it is a very simple figure, but this is something will happen for 4G and 5G, and will be for 6G. So we have base stations, we have cells, we have several users, and we have maybe we need to multiplex users, and we see interference from different cells. So the desired key performance indicator is network spectral efficiency. I think probably the most relevant KPI related to operating a wireless network. Typically, we assume 10 times network spectral efficiency or more. But how can achieve this? So let's go to the critical problem. Given the same number of base stations, what shall we do to achieve better network spectral efficiency for 6G? So we can note the condition is that we assume the same number of base stations, because of course we can add more loads like a relay and small cells into the network. But according to the experience in 4G and 5G standard, it's not very successful. I think the reason might be first, the site location are very difficult to get, because it's quite expensive to get a new site or massive site to enhance the current network. The second, because the new network load are not massively deployed, then the cost of this new network load even maybe relatively simpler than the regular network load, is still quite expensive. So this is why we assume the same number of base stations. Then we talk about how to achieve better network spectral efficiency. Okay, go to a little more details. So we can see from 4G to 5G to 6G, we have a frequency band sort of increasing, and for baseband antennas is increasing as well. And for the MU-MIMO techniques, it's always SDMA for 4G and SDMA for 5G. And of course, we will have a increased frequency band for 6G, and likely the base station antennas for 6G. So the technique would be SDMA as well. So we go to observations. The answer seems very simple. We just deploy more antennas at the base station and go with SDMA. Probably we go to the answer too quick. Let us think more. So then we go to 3GPP activities. That's quite a lot actually for this aspect. First, let's have a look on what happened recently in 3GPP about MIMO and MU-MIMO. So we can see this logo here. It's 5G advanced, what we can understand as 5.5G. And there's a new ongoing, and this the first release will be release 18 as ongoing work item on MIMO and MU-MIMO with this T-dot number. This is there's some descriptions copied here. I think it's quite a lot of details, but we can get some impression from this highlighted text. So we can see from justification part, there are 6 points mentioned. So we can see this first point for high mobility, and the second is for overhead and latency concerning multiple TRP operation, and third is for larger number of layers, should be for MIMO layers and MU-MIMO layers. So this issue. And fourth is enhancement for coherent joint transmission. It's like a comp and multiple TRP transmission. And the point 5 and point 6 is sort of for uplink transmission enhancement for more antennas and more code words. So if we group these 4 points, we can see some keywords like high mobility, more layers from for UE scheduling and uplink enhancement. So this is something we can get. If we see from the objective part, you can see some keywords. There's a enhancement both on downlink MIMO and uplink MIMO. You can see some keywords like CSI enhancement and high mobility and larger number of DMS ports and uplink DMS SRS for higher number of larger number of antennas like that. So all in all, we can get observation is that 3GPP is specifying MIMO and MU-MIMO enhancement still based on SDMA in its latest version. So then if we may need to have a look at from the very beginning is the first release in LTE. So the first feature we can mention is SDMA. So in this figure is very clear. So if we have 2 users, then we can multiplex them in time domain with the simple scheduling strategy. This zero forcing strategy. This means that for the intended user transmission, the precoding direction is intends to zero the interference to the paired users. So there will be some mismatch between the precoding direction and the channel direction of the intended transmission. But the solution is quite clean and simple. Then we see what happened in LTE release. So we can see that SDMA in LTE, they actually be introduced in release 8 and will be enhanced in release 9, 10, 13, and 14 with the increasing number of antenna poles at that base station. This means that even more high spec base stations in terms of antenna, and they support more MU-MIMO layers in different release. It is the trend. And this put downlink as an example. So we can get the observations here is that SDMA is natively supported from the first LTE release and largely used in product. And 3GPP continues to enhance SDMA by multiplexing more layers. So there might be some also potential issues that SDMA needs good spatial separation from UEs, which may require strict UE pairing. For example, if the UEs the spatial direction is kind of highly correlated, then that might be an issue. And also SDMA is based on the CSIT, the channel state information at the transmission side, which may be sensitive to UE mobility. Now, the other feature is ICIC in LTE. ICIC means that inter-cell interference coordination. So it's first introduced in release 8. So for this figure, you can see that for the cell edge users, this can be scheduled with partial bandwidth and in a coordinating way. For example, for the label cell, they can schedule a different partial bandwidth, and the interference can be avoided in frequency domain. And for cell center users, they can just be scheduled with full bandwidth because there will be slight inter-cell interference perceived. And this concept is further enhanced in release 10 and 11 is enhanced in ICIC and further enhancement. And the main additional feature is this ABS, almost blank subframe. This means that on top of normal subframes, an ABS subframe will be introduced, while restricted signaling signals and channels or power will be supported in the ABS, meaning causing less interference to neighbor cells, and in this ABS, neighbor cells can schedule in transmission with reduced interference. in this way, the interference has been controlled in a better way. So get this observation here is the ICIC and its family. We use time and frequency mainly for inter-cell interference. And this technique not considered as a key solution in improving network spectral efficiency. And we see some potential issues as well, is that the coordination between base station is typically slow and not adaptive to instantaneous channel status. So, and also the time and frequency we use, especially long-term correlation based, is inefficient. Oh. Then we go to COMP. In LTE, COMP means coordinated multi-point transmission, and further introduced in Release 11 and enhanced. I think Release 11 is mainly for intro base station COMP, and Release 12 is in enhanced COMP, is for inter base station COMP, and for Release 15 is further enhancement COMP. It's kind of support of non-coherent transmission from different points. Now, two concepts I think in COMP. First is the joint transmission, is that two cells are transmission data simultaneously. And there's coordinating, sharing, and beamforming is that data just from one cell, but the sharing and beamforming decisions are coordinated between cells. So the observation here is that COMP mainly makes use of spatial domain coordination to deal with inter-cell interference. And for commercial use, only intro base station COMP is largely used. The issue is that several challenges, especially on information and data exchange between transmission points, as well as synchronization, will happen, especially in inter base station COMP. So there are also NICs in LTE. This NICs means network assisted interference, cancellation, and suppression. And this feature only specified in Release 12. So it's a small feature. The steps is like there's three-step procedure. First, a neighbor cell will send some sharing information to a serving cell, and the serving cell, based on this information, as a step 2, will send network assisted information to a user. And at step 3, this user, by receiving the data from the serving cell and interference from neighbor cell, will make use of advanced receiver, and also with the help of network assisted information to cancel the neighbor cell interference, and then you get the serving cell data. So the observation is that advanced receiver for spatial interference handling is supported for NICs with the help of network assisted information, and NICs is not used widely. Potential issues for NICs is that we see no significant benefit for NICs over advanced receiver only solution. That means that we just use advanced receiver without NICs. The performance is maybe just as good as NICs. And there's also the feature is the MAST in LTE. MAST means the multi-user superposition transmission. This is specified in Release 14, and there's no further enhancement. It basically means that there's maybe a small feature. So MAST here in this figure is that the base station is for downlink, schedules superposed information for the near UE and the far UE. So for the far UE, actually is power allocation is high, it's more power, and for near UE it has small portion of power here. So for the near UE, since the geometry is good, so it uses interference decoding, so you can decode both decode the far UE information first, and employs interference cancellation gets its own information. And for far UE, it's only it can just take the near UE interference as noise and treat interference as noise. So the observation here is that the power domain domain is used, and near UE decodes interference, and far UE treats interference as noise, and must is not commercially used in product. There's potential issues is that we need a strict user pairing actually must. Then we go to 5G. So still the first release feature is SDMA, but maybe it's on the scope of Massive Mimo. So if we have a Massive Mimo base station, then we will basically means that we have finer spatial granularity. Now in this case, it can help to avoid interference. The precoding can be made in a better match to its own channel condition. Of course, if we have a huge amount of users, we can pick some good pairing UEs, and we don't schedule in this less good. This maybe this UE with maybe more worse this spatial separation. So we have a better spatial granularity. We may have a even larger number of users. Then we can have better SDMA with Massive Mimo. And in 5G, SDMA is supported from still the same thing, supported from the first release and enhanced almost in every release. And the network is designed in a very flexible way. You can see that even in release 15, the antenna ports, network antenna ports is arbitrary. It's in a way that it can configure more than one set of CSI-IS ports. And for this MU MIMO layers, is still for the release is kind of as a high spec. It supports high order of 12, and it will be considered to be further enhanced in release 18. And the observation here is SDMA Massive Mimo is natively supported from the first NR release and largely used in product. And also SDMA Massive Mimo will be considered as the key 5G technique and further enhanced in later release. So also in this technique there might be potential issues that SDMA Massive Mimo relies on fine spatial separation, which needs a sophisticated CSI framework and sensitive to mobility, which might be a noticeable issues. And now also there's a famous technique is NORMA. NORMA means non-orthogonal multiple access. So this kind of it also take downlink as example is kind of more complicated than must in LT. So you can see that the base station schedules a set of users, and these users are multiplexed by power, especially mainly by power and code domain. There's a huge number of normal schemes discussing on 10 plus, more than 10. Yeah, let's take SMA as an example. Is that here you can see that there are 6 code books and 6 users, which use one, maybe up to 6 users. One use each SMA code book, and multiplexing 4 frequency resource. So it kind of overloading. and this is power and codomain multiplexing. And the observation is that normal is extensively discussed in 5G, especially from code and power domain. But you can also, the outcome of 3GPP is that normal is not supported in 5G. So there should be some potential issues that normal will need good user pairing, and it's not clear how efficiently normal works with massive MIMO. And also there might be advanced receivers assumed. So in this page, I give a summary here. This table, it shows that only SDMA is MIMO and massive MIMO is largely used. Other features is kind of not used or just small used. So get to points that SDMA is specified heavily in 3GPP and used widely in product. And its techniques deal with mainly the serving cell interference. And it's done also called multiple access technique, mainly for spatial domain. And it needs accurate CSIT and C challenges in massive MIMO mobility and FDD massive MIMO. But we still need to maybe see or foresee that SDMA likely continue to be the key technique in 6G. And neighbor cell interference handling techniques also studied in 3GPP, but not really very successful. This ICIC and its family explores frequency and time domain, and NICE and COMP explore spatial domain. And normal studied in 3GPP, but not really used. The power and code domain explored, and must specify in 3GPP, but not used. A normal is even not specified. So we can move to these research activities. I will give a short review on what happened in research. So first we talk about the subtle bond and dirty paper coding. And there's some reference listed here to show first, MU MIMO capacity is upbounded by SU MIMO capacity is easily understandable. For example, if we take these two users as just one user, then there's ideal cooperation between users. Then this MU MIMO capacity should be goes to SU MIMO. And the second point is that it has been shown that DPC achieves subtle bond. Yeah, in this reference, it shows that the DPC rate is equals to subtle bond and equals to MU MIMO downlink capacity. But it's well known that DPC is nonlinear processing, so it's considered very complexity. It may be not acceptable for massive MIMO. For this, the additional step is for zero forcing beamforming. I copied the text here. Is the zero forcing beamforming strategy. Well, generally, suboptimal can achieve the same asymptotic sound capacity as that of DPC as the number of users goes to infinity. So I think this can be explained by this figure. So if we have a huge number of infinity number of users, you can always find a good spatial matching user, and they can spatially separated, and also the precoding can be a good matching to its own channel condition without SNR loss. So the observation is that ZFBF seems nice for MU MIMO. There's no complexity, capacity achieving. So probably the 6G shall use SDMA like 4G and 5G. So probably we just go to the answer too quick. Let us think more. Summary is that researchers have shown that DPC achieve MU MIMO capacity at cost of high complexity. They also show that ZFBF approach DPC in terms of capacity with no complexity. So they are quite forward-looking in this aspect. And 3G, 4G, and 5G both speed MU MIMO based on ZFBF. It may be necessary to review this conclusion as MU MIMO solution is critical to 6G. The points assumes in the research needs to be known, may not be typical in the case in cellular networks. It's infinite number of users and IID reunificating channel and perfect CSIT and zero cell interference. So let's move to our focus for RSMA. So this opportunity and challenge for 6G MU MIMO. Look at the general principle of RSMA. So different from, this is a case for, I think this is the concept illustration raised in 1981. So different from the previous, different user just send its own private information as common information transmitted as K and M. And on the receiver side, the receiver first decode the common information K and M, then seek the common information and then decode the private information. And this concept has been also used in Mimo BC system in this reference. I think it's a non-trivial effort. So for this Mimo BC system, we need to also split the message with, we have this common message and private message. And at the receiver side, we first seek the common message and get the private message. So RSMA can be considered as a smart solution for interference decoding and treating interference as noise. So we need this capability. So now we go to the details of these opportunities. So I think opportunity one is related to marginal utility. So I think the marginal utility is a common used terminology in economy. But it's also, I think it's applicable to many cases, many things in our daily life. This, if we go to MIMO or mass MIMO, or even extremely large mass MIMO, the formal introduced MIMO antenna gives more utility than the later. So if it goes to 3G, LTE, 5G, and 6G, so we can see that LTE SDMA should have the sweetest point. And if it for 4G, 5G, and 6G, we need more effort to achieve the similar spectral efficiency gain. Let's go to more details. And in this figure, this is NR 5G NR downlink DMR is a demodulation reference signal illustration. So you can see that we can only use this type 2 DMRs to support a maximum 12 layers for MU MIMO. So we need a maximum 12 DMRs patterns. And to support this maximum 12 DMRs patterns, the overhead is at least 14%. So there's practical issues that if you want to support 100 and above layers, and how much overhead will be consumed by DMRs. maybe it's already 100%. So we don't have a space for data transmission. And also there's more aspects causing marginal utility. This may comprise processing complexity. We know if we increase the scale of antennas, the processing complexity does not scale. That does increase linearly. It's a kind of it's a power of 3 at least increase. And also there's sounding referencing signal overhead is critical to TDD massive MIMO performance. We need to sounding referencing signal to measure the channel. And also the spatial correlation, if we have a lot of antennas, if we actually has a highly spatial correlation, then maybe you don't have a significant gain by increasing the antenna. And also we have an antenna array size limitation, and we only have a limited size for base station antennas, so we cannot actually arbitrarily increase the number of antennas. So let's go to the opportunity 1. Now, the 6G antenna scale goes even massive, while spatial and marginal utility may be more noticeable. This may leave good room for techniques like RSMA. This boosts the network spectral efficiency from a new way. And opportunity 2 is, I think, is maybe a way out. Is that from a technical point of view, is that RSMA explores new areas outside of existing 3GPP study. In the review of what happened in 3GP, we see that a lot of techniques and features has been specified and studied extensively for spatial time, frequency, power, and codomain. But RSMA actually is brings some new area. So this may have a new chance actually. So let's go to the 3GPP opportunities that 3GPP has done a lot. RSMA could be possible way out if by exploring the rate area, which is kind of outside of existing 3GPP study. And for opportunity 3, I think this RSMA can address technical issues and robust to non-ideal cellular network condition. Yeah, we have 4 cases here. For example, it's a finite number of users. We usually we do have certain number of users, but we not increase significant for 6G, and also for real scheduling, there might be case that a very limited number of users have data to transmission. So in case for this case 1, only these 2 users have packet to send, and they're not actually good separated in spatial domain. Now what we should do? And for the second case, for the case 2, this is the case that, for example, for hotspot scenario, that's not have users located very close to each other. And in this case, usually spatially highly correlated. Yeah, this might be also not friendly to SDMA. And for high-speed mobility use, as mentioned earlier, is a big issue for SDMA, especially for high order Mimo case. And for scenario case 4, and in this case that we have a MU Mimo for serving cell, but we will face interference from neighbor cells. But SDMA does not have a capability to deal with label cell interference. So for this 4 case, you can see SDMA is not very good, and RSMA may may be more robust. So this opportunity 3 is that RSMA addressed an institute ideal assumption problem of SDMA, and thanks to the proper interference handling capability. And then we go to challenges. If we actually see the milestone of RSMA, then we can get some hints of these important issues to address. So I think in the year of 1981, so the concept is raised, and it remains still the best achievable bond for IC channel is HK bond. But the to-do list, this includes input signal distribution is not known, and how to split rate and power, and rate splitting for MAC and rate splitting for BC, because it is rate splitting for IC. And in the year of 1996, the RSMA for SISO MAC is addressed. And then the to-do list, we have additional one is rate splitting for Mimo MAC, and it's the remaining ones. And in 2008, there's a simple input signal distribution and rate power split. This solution is raised, and then there's a ETW bond, which will be explained further in later. And for the to-do list, we have remaining is the optimum input signal distribution and optimum power and rate list. And also this is remaining. And in the year of 2015, so RSMA for Mimo BC and precoding algorithm and optimum power and rate split have been addressed. The to-do list is the optimal input signal distribution and no complexity precoder and rate splitting for Mimo MAC. So you may see at least these 3 points to be addressed. And the first challenge, I think, is the remaining question for rate splitting RSMA is that what's the best input signal distribution? This in this reference 2008, there's assumption is that the simple assumption on this random Gaussian input, and also there's a power split here. So based on a simple assumption, they get a ETW bond, and actually for illustration purpose, the HK bond is provided here. So it is claimed as very close, but we don't know. This is for 2 user case, so we don't know for Mimo, not number of user case. And there's also maybe some way out here is that there's a work in 2013. It has been shown that if we adopt improper Gaussian signaling instead of a Gaussian signaling, then that's a capacity gain here. I think to understand this is that Gaussian signaling provides the maximum entropy. It's always good in case there's no interference. But the improper Gaussian signaling provides additional design freedom by not mandating this IID-IQ branch of signals. Hence, this IGS may provide better capacity in Mimo case if interference exists. So the observation here is that the optimal input signal distribution remains unknown. This might be an additional design freedom, which should be further investigated. And for challenge 2, so this is about no complexity precoder. So we, in my view, the RSMA targets extremely large Mimo. Well, no precoding complexity is crucial. This is we see this figure again. So you can see that SDMA has been supported in LTE and for 5G. So for this conventional antenna setup, SDMA works well. And for RSMA, it's likely that it has to be coexist with extremely large MIMO. So that's the case or basic assumption for RSMA. And in that case, the precoder complexity will be a big concern. So this has to be addressed. And also in this reference, that shows that there's a different precoding strategy even for SDMA. So you can see that GFBF is kind of zero interference, but we have optimal beamforming, which targets the best SINR instead of just taking care of interference purely. So optimal beamforming is good, but observation is that, but it's not used. So we get several observations that SDMA has been very successful in 4G and 5G. So same setup, same solution. And one critical benefit of SDMA is a simple implementation of the GFBF precoder. GFBF even not as good as optimal beamforming wins in previous in previous usage. And the major difference of 660 MIMO is XL MIMO, and no complexity will be a key. So RSMA, if introducing 60, will be likely to be designed based on this XL MIMO. And no complexity precoder, at least at a similar level to GFBF, will be needed. And this challenge is 3, I think, is for RSMA uplink. And this also I think is critical for RSMA as a 6G solution. This reference shows that the design targets of 5.5G for uplink capacity is 10 times requirement. So in addition to these 3 cases for 5G, and there's 3 important cases also raised for 5.5G. And here we can see that for this HD video uploading and machine vision service, we need uplink performance enhancement. And techniques mentioned here mainly include this high resolution uplink precoding, high order spatial multiplexing, and multiple TRP operation is still in the way of SDMA. So SDMA has uplink enhancement, but what we have for actually RSMA for SISO-MAC, I think maybe we can have a look at what happened in 1996. Now here for uplink is it's very, I think the solution is very initial. It's just the user split their transmission, their message into common and private part. They apply maybe different power control, and at the receiver side, very complicated receiver by canceling users one by one or layers one by one. Yeah, but so it's very initial. So we get some observation here is that uplink experience has been a key design target in the ongoing 5.5G standard. We would like to become even more important 6G because the traffic status has been changing. Uplink will be more central points and more required in 6G. But it's not clear how RSMA uplink works, especially for XL MIMO. To fit the 6G timeline, XMIMO based RSMA uplink needs to be given higher priority at this stage, probably by exploring new areas on top of CGPP. So then maybe I can go to the overall summary. So first is a critical question. Given the same number of base stations, what shall we do to achieve a better network spectral efficiency for 6G? And we have the industry answer. It's SDMA. And we may have some points. Noticeable is that SDMA is specific heavily in 3GP and used widely in product, and likely continues to be the key technique in 6G. Now, SDMA mainly explores spatial domain and dealing with intra-cell interference. And neighbor cell interference handling techniques is not actually, they explore frequency and time domain, but not really successful. And normal studied in 3GPP, but not specified. And power and code domain and explore. The researcher answer is still SDMA. At some points noticeable as DPC achieves MU-MIMO capacity, but its complexity very high. And JFBF approached DPC in terms of capacity, which is reduced and no complexity. However, the assumption for the above points may be too ideal. And we also have a RSMA answer from our side, is that RSMA probably with the following opportunity and challenges. And the opportunity is that spatial marginal utility in 6G may need good justification for RSMA, which boosts the spectral efficiency at a different angle. And RSMA may be a good technique way out for a 6G MU-MIMO by exploring rate area outside of existing 3GPP study. And RSMA addressed two ideal assumption problems of SDMA, thanks to this proper interference handling capability. And I also some challenges here is, I think first is the optimal input signal distribution. It still remains unknown and needs to be investigated. And no complexity RSMA precoder. This would be crucial because extremely large MIMO will be assumed. So no complexity receiver, at least at the same level, a similar level of CFBF complexity, lower, better, shall be targeted. And for RSMA uplink is, I think it's pretty mature, premature for now. And it's crucial to make RSMA as a comparison solution for 6G MU-MIMO. I think this basically concludes my presentation.
Thank you. Thank you, Dr. Wang, for the very informative and very comprehensive talk. I really enjoyed it. Thank you very much. Your summary is super clear, to be honest. I believe Bruno liked it very much.
Yeah, I enjoyed it a lot indeed.
Yeah.
Thank you.
So any questions from the audience?
I have some questions, if I may start.
Yeah, sure.
So thanks again, Van Wang, for this very nice talk. I was wondering, what are your thoughts on RSMA for other scenarios that may not require massive MIMO? And I'm thinking of maybe scenarios like in maybe emerging satellite applications where you may have many more users to serve than the number of antenna elements that you have available at a transmitter, maybe in satellite. So this is one scenario. Or another scenarios would be maybe where you have a mixture of traffic, unicast and multicast and broadcast, all mixed up. Currently, those are separated, I think, in the standard where unicast and multicast are done on orthogonal resources.
Yeah, thank you for the question. I think I actually make the talk in a commercial usage way. Actually, the commercial usage of 6G features will be step by step. And the first step, I think it should be the most important. We have a full coverage network with similar or the same number of base stations, and we suppose the extremely large MIMO. And we built the 6G techniques from the very beginning based on extremely large MIMO. And then we support some techniques, especially for MU-MIMO techniques. If we can support it, for example, RSMA here, it's will be a very big thing. And for these techniques, for example, in this satellite, yes, have a lot of users, and they maybe also have this multiplexing. And for this broadcast and unicast scenarios, I would see this race splitting will be still a very good, maybe an even better fit. But maybe one thing needs to be considered is that for those scenarios, maybe the first thing is still to support this extremely large massive MIMO. So if MU-MIMO techniques has been specified from the first release, then it might be at more difficulty in introducing a different MU-MIMO techniques. So technique-wise, I would see rate splitting is very
Am I the only?
Yeah, it's also the same issue from me.
Yep, it's for everybody.
Let's wait for him. Let me call him.
thing. Oh, sorry. I'm not, yeah, I think I rejoined.
No worries. We can hear you now.
Okay.
That's good.
Okay, good. I'm not sure whether my response has been actually.
You started talking about the unicast and multicast, and then you were saying that I think the extra massive MIMO is really essential.
Maybe I just re-answer again. Yeah, sorry. Yeah, I'm trying to say that this I think technique-wise, this rate splitting is very, I think, is sensible for this satellite case and this multicast and unicast scenario. But the thing is that, but from standard wise, the standard procedure wise, there might be, I think the first priority in standards from first release is that there will be a MU-MIMO techniques specified there for extremely large massive MIMO. So if we have a first release supporting this feature and we already have MU-MIMO techniques, for example, as SDMA, then it might be very difficult, more difficult to introduce different rate splitting, different MU-MIMO techniques. So the best thing is that we already have it in, for example, RSMA have it in the first release.
Right. Okay, thank you very much.
Thank you.
Okay, so we have one question in the chat box. So the question is, will you suggest any best, sorry, this is not related, the best materials or videos? Okay, so for videos and materials, you can find it in our website, RSMA website. Okay, so Dr. Wang, I actually have one question related to, because you mentioned the research challenges of RSMA, and my question is that the use of SIC in, I mean, maybe for the future MA, do you think is still a potential challenging, and what's the number of tolerable SIC you can see at the receiver side?
Yes, I think next question I think is also related to this Mimo scale. For example, if we have a very large scale of Mimo at the base station side or at the UE side, then we will bring a lot of complexity. So if we can have some kind of reduced complexity solution for this spatial domain, then it's possible you can support this SIC because this kind of overall complexity will not be increased too much. So it's kind of overall design, I would say.
I see.
So this is why I think this low complexity precoder is important thing. Is when you talk about
you think that the low complexity should be as low complexity as ZFBF, right? Comparable.
Yeah, it's comparable. Yeah, if you can design a solution, actually, if you have a precoding procedure is or receiving procedure is of very low complexity, then why not support SIG?
Yeah, so the issue is that if we consider such low complexity, we also, suffer from the rate loss compared to the, the optimized results. So do you think? Yeah. I mean the tolerable range of the decrease of the rate, do you think is reasonable?
Yeah, I would say maybe the no complexity is a mandatory feature needed for this extremely large Mimo. But we actually in commercial use we do see the performance loss if we adopt this practical algorithms. So I think it would be possible to support SIG, especially for if we can actually support some kind of less complex spatial operations. So we do not want to actually have a much increased complexity, especially for this high spec Mimo scale. So if we introduce something in SIG domain, maybe we do less in the spatial domain. Let's do it in a combined way.
Okay, thanks very much for the explanation.
Thank you.
Any other questions? Bruno, you are muted.
Yeah, maybe one last question for me. So you mentioned about this overhead of DMRS if you start transmitting many streams.
Yes.
So do you think there is a plan in SIG to get rid of some of those DMRS and rely on some form of channel hardening that we have in massive MIMO? Or do you think that there could be some benefit for RSMA to essentially operate in scenarios where maybe we have fewer DMRS? I don't know, I'm just trying to extrapolate a little bit, right? Given the I mean, the DMRS introduce, if you don't have enough DMRS, then you introduce imperfect CSI at the receiver, which may be an issue for many of those multi-user processing techniques. But maybe there may be some benefit because of the inherent robustness of rate splitting to cope with fewer DMRS than SDMA, for instance. I don't know. I'm trying to have a sense there of what your opinions are.
I would say these both are possible alternatives. If we have even a massive scale, even more antennas, In this way, because we do not see channel hardening actually in 5G. So if we go to channel hardening, then we'll see severe performance loss. And if we go to even more antennas, we don't believe channel hardening will be actually very accurate. It would be a very core solution. But if we don't have DMS, what can do? It might be one possibility, but we see a lot of performance loss. And for RSMA, I tend to agree that this will help a lot to deal with these DMS issues if we have introduced some, if we don't just support just a few DMS, or if we support DMS with this non-orthogonal DMS that's interference there. So I would see this will be a very potential directions to address if we build this based on RSMA framework.
Right.
Okay.
Okay. Thank you very much.
So
Thank
if
you.
there is no other questions, then I will end the webinar today. Let's thank Dr. Wang again for a very, very comprehensive talk, and thank you all for attending this webinar. And at the end of the series of this webinar, I would like to remind you guys that we are actually going to organize some tutorials in this year's ICC WTC PIMRC, and also special issues of rate splitting will be coming soon. So we will keep you updated and via the main website of RSMA, and which the link is provided in the chat box already. And we will also notify you via the ComSoc mailing list. All right, so thank you all, and thank you, Dr. Wang. Bye-bye.
Thank you.
Thank you, Dr. Wang. Bye-bye. Thank you, Lina. Bye-bye,
Thank you,
everyone.
Yeah.
bye-bye.
Yes,
Thank you,
hello,
Dr.
madam.
Wang.
Bye-bye.
Hello, madam. Hello.
Yeah, I'll take care of this. Hi, Rajshekhar.
Nice.
You can talk to me offline. I'll give you my email address. Just a second.
Okay, sir. Sir, I want to discuss some 2-3 minutes. That's sir.
Sure.
Shall I talk now? Shall I discuss now?
This is being recorded.
Sir.
I'll give you my email ID in the chat box.
Sir,